Hello everyone. Today we will talk about the work energy theorem. Okay, work energy theorem. So, what the work energy theorem says is, let's say that you have 2 points in space. Very general case I am considering. All right. Let's say I have 2 points in space anywhere, and you are considering a path. Okay, you are considering a path along which you are taking, let's say, a particle of mass m, which is being moved along this path. Okay, let's say that there is a particle, let's say there is an object, a block, whatever. You are taking that object and you are moving that object from point A to point B, and point A and point B are anywhere in space. So here is point A, here is point B. You are taking some object and you are moving it along this path, along a particular path. Alright. Let us say that there are several forces acting on this particle, and let's say that due to all of them, the force which is acting over here is F. Okay. Let us say that this is the force which is acting on this one. And due to this force, there is a slight displacement of this particle, let's say ds, and now this particle is k, right? So if we talk about the work done here, what will be the work done? dw is going to be f dot ds, alright? And we can always say that then the total work obviously is going to be what? It is going to be the integral of dw. W is going to be integral of dw, so that's going to be integral of f dot ds. Alright. Now, what we could do here is you can take the force as m dv by dt, or you could also take it as m v dv upon ds. Okay, you can also take it like m v dv divided by ds. That times ds. Okay, that dotted with ds gets cancelled. Okay, ideally I should be expanding this. This will be fx plus fy plus fz ijk. Then this will be dx dy dz ijk. Then you will have actually 3 terms, and we can say the same thing for all these 3 terms, but we are considering a simple situation. Okay, let's just take one term here. So what is this essentially? You can see that this is mv dv. Yes or no? So from here you find that the work done W, that's going to be m times integral of vdv. Alright. Now, what is the initial position of the particle? The initial position of particle was here. Final position is, let's say, here. So the initial speed of the particle is va, and the final speed is vb. And from here you see that work done can be written as, what is the integral of vdv? V square upon 2. So this will be m vb square by 2 minus m va square by 2. vb square by 2 minus m va square upon 2. Right? Which means the work done W, this is what? Kinetic energy at point B. This is what? Kinetic energy at point A. So this is going to be Ke at B minus Ke at A, or delta Ke, and this is your work energy theorem. This is very important theorem. This is your work energy theorem, that is the net work that is done on this particle as it moves from here to here has to be equal to the total change in kinetic energy. Alright. Now let's consider an example relating to this. One example we'll consider. Let's say that you have a pendulum bob over here, right? Let's say the length of the pendulum string is L, mass is m, and let us say this is given a speed of u. Okay. Question is find find maximum angle made by bomb. Okay, so if I give it the speed over here, then what will be the maximum angle made by this bomb? Okay, so how do we calculate that? Just imagine that because of this impulse given here, this bomb is going to move by an angle, let's say theta. Okay, now if we talk about maximum angle, what it means is that at this point the speed is going to be simply 0. Okay, so if you find delta K, change in kinetic energy, what is that? Final kinetic energy, which is 0, minus initial kinetic energy, that is half mu square. I'm writing it here, half mu square. And this has to be equal to total work done. Now, how many forces are here? As you can see, as it moves from here to here, there is of course the tension, and of course there is the weight acting in the downward direction. So now you can see that tension is acting in the radial direction, and this bob is moving in a tangential path. You could say arc of a circle path. So we can say that the angle made by this tension and the displacement of bob, angle between them has to be 90 degrees, right? Or we can say that T dot ds has to be 0, alright? Or you could say that the work done by tension is going to be 0. So work done by tension, work done by weight, this is not there, alright? What about work done by weight then? Work done by weight will be mg times whatever height this is, h. Okay, now on calculation you will see this is L cos theta naught is this length from here to here, and this is the total length. So h is actually L times 1 minus cos of theta. Alright, so we can put it back there. So this comes out to be minus half mu square is equal to minus mgl into 1 minus cos of theta naught. Minus because it is moving in the upward direction. Okay, the weight vector is acting downward, displacement is in this direction. Okay, the angle will be obtuse, therefore the work is going to be negative by the weight. Now if you evaluate this further, you can see that negative gets cancelled, gets cancelled. You have u square is equal to 2gl times 1 minus cos of theta. And here you can see that cos theta naught therefore is going to be equal to 1 minus u square upon 2gl. Yes or no? Right? So from here theta naught is equal to cos inverse of 1 minus u square upon 2gl. And this is the angle, maximum angle till which the bob is going to go. Alright? You can see that this is a direct application of the work energy theorem. You can use conservation of energy as well, that can be also done, but essentially both are the same. Conservation of energy, delta K plus delta P is 0, can be derived even from the work energy theorem. Okay, so both methods are correct. Alright, so this was an example of the use of the work energy theorem. So that's it. Thank you.